Hello, ladies and gentlemen. It is your daily dose of Dorfler here with part two of Great Timing, always with the bell. Part two of section two of chapter 5. All right. So, in the first part of section two, we got into kinetic energy, and we also saw how network can be related to kinetic energy and how we can substitute in certain variables and show the relationship there. What we get into then is what's called the work kinetic energy theorem, which is what we're going to be taking a look at today. So we're going to be combining a couple of things in today's problems. Okay, we're going to be taking a look at how we can relate the formula for net work, which again we saw was net force is multiplied by distance. And we also saw that the change in kinetic energy, which also equals network, how those two, when they're, if those two things are set equal to other items, therefore the other items should equal each other. Think, you know what I'm saying? I'll show you what we're going to show in a minute. Anyway, what the work kinetic energy theorem states is that the net work done by all forces acting on an object is equal to the change in the object's kinetic energy. So the net work done on a body equals its change in kinetic energy, as we see here. So what we're actually going to do is we're going to be essentially utilizing the two formulas that we have seen for net work, which again, if we go back here, okay, is this. Here's our first network one where we have force times the change in displacement of the object, which could also be mass times acceleration. We can also have it as net force is equal to the change in displacement, or as we'll see in our sample exercise, how we can utilize the concept of kinetic friction to help answer our problem. You have to read the questions carefully. And one note, if you have to use, or if you're going to use the net force in your calculation, and you're given two values for forces, for opposing forces, think about how you have to get the net force of that. You have to take the difference. Hint, 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 maybe number 3 of your homework. Anyway, so let's take a look at our problem here. We are on a frozen pond because that is always safe. We have a person who kicks a 10-kilogram sled because they're so mad, giving it an initial speed of 2.2 meters per second. Now remember that speed needs to be in meters per second, mass needs to be in kilograms from last video. How far does the sled move if the coefficient of kinetic friction between the sled and the ice is 0.10? All right, so what do we know? We know that the mass of the sled is 10 kilograms. It has an initial speed of 2.2 meters per second once he kicks the sled. And so we need to figure out how far does that sled move. That means that eventually, from the moment that that person kicked the sled to how far it moved, it came to a stop. So that has to kind of be kept in the back of our heads when we are solving these problems. Okay. And lastly, we know that the coefficient of kinetic friction is 0.10. All right. So again, here's everything that we know. Initial was 2.2 meters per second. The mass was 10 kilograms. The final speed was 0 because it came to a stop. Again, we're making that assumption. And their coefficient of kinetic friction is 0.10. We need to find out how far did that sled actually travel given those parameters. All right, so one thing we need to look at is the individual formulas themselves, okay? The net work formula we saw last chapter has net work is equal to net force times displacement times the cosine of theta, okay? But in this particular instance, for this example, the net work that is actually done is provided by the force of kinetic friction because it slows down. Because it is slowing down and comes to a stop, we have to think about the net force being in terms of the frictional force involved. So, again, this goes right along with what we've done previously in the last chapter. Net work is equal to the force of kinetic friction multiplied by displacement times cosine of theta. But if we really wanted to break this down, the force of kinetic friction can be solved by taking the coefficient of kinetic friction, that mu k, multiplying by the mass, multiplied by the gravity, okay? So, and then we take those and multiply it by d cosine theta. So basically we just took this, the force equation, and broke it down into mass and acceleration due to gravity, and included the coefficient of kinetic friction, because that is our force in this instance. It's not always going to be that way. You have to read the question carefully and decide what is happening to that object in the problem. So that's the first part right here. So we know that net work is equal to mu k times m times g times d times cosine theta. Lots of stuff, okay? So honestly, you got a couple formulas you're going to need to write down here, okay? If you want to, you could start off with this. Net work is equal to the change in KE, and then just continue to add where we have net work is equal to net force times cosine of theta times d, however you want to say it. But you can also include that if there is a frictional force that is the net force here, then you can put these formulas down here as well. So that's really half of the problem, as I was saying. Next thing is we have to look at the change in kinetic energy. We saw this set up. I'm going to go back a few slides here, okay, where net work is equal to 1/2 mvf squared minus 1/2 mvi squared. But in this instance, since our final speed is 0, that means this whole half of the formula will be 0, and we're just left with this negative 1/2 mvi squared, as we see right here. So since net work is equal to this, negative 1/2 mvi squared, and it's also equal to mu k mgd cosine of theta, that means that since those two, since this right here, if you see my arrow, and this are both equal to net work, that must mean that they can be set equal to each other, which is what we see right here. Okay, ultimately, now again, this is another good one to write down, but I would also include the 1/2 mvf squared in conjunction with this. That way you can see the entire thing. So if you want to add this, is 1/2 mvf squared minus 1/2 mvi squared equals mu k mg d cosine of theta for this particular one. Otherwise, this might just be net force, or F net d cosine theta. Lots going on here, but they all are related to each other, okay? So the whole premise of this problem is to determine the displacement of the sled, the distance that it traveled. And so we have to rearrange this to solve for d. And so once we do that, we can then go ahead and solve. But one thing I want to point out for you is this. The force of kinetic friction, we talked about this in previous chapters, it's always going to be exactly opposite the direction that it's going. So if a sled is moving forward, the kinetic friction is going to be acting in the backwards direction. So its theta will be 180 degrees because it's exactly opposite of the forward motion. So we plug in our values here, and we get a distance of 2.5 meters that the sled has traveled from the moment it was kicked to the moment that it stopped. So not too terribly far. So it's just a combination of some things that we've covered over the last chapter. Stuff we covered yesterday and stuff we covered in the previous chapter. Just putting them together. Read the questions carefully. Now, you're only going to have 5 questions for homework, okay? So if you have any questions on any of the 5 questions, let me know, okay? And I can kind of help you through that. But what I'm going to do now is I'm going to let you to it. I will be attaching along with, actually, I'll probably making a separate post right after this video with your homework That way things don't get lost between videos and homework assignments. I think that may have been the culprit earlier in the semester. So I'm going to try to separate homework assignments from your notes or materials or anything like that, just so they stand out. Okay. So I'm going to stop this video. I'm going to get it posted, and then I'm going to also post your homework. Have a good day, everybody.